yours now.
Okay, thank you for the detailed introduction. Thank you, Adi, for the invitation to speak, and I guess selamat pagi to everyone.
Selamat pagi.
And thank you for joining so early. So I'm just going to share my screen so you can all see what's going on. So can you see that?
Yes, it's clear.
Fantastic.
Okay.
Let's maximize that. Okay. So even though there's been an introduction on my background a bit, I'm just going to give a bit more of a information about myself. Okay, so of course I'm in Singapore now, but actually I grew up in a small town in Australia. So this is where I'm from, Griffith. It's about 600 kilometers away from Sydney, which is over here, which everyone seems to know, and about 400 kilometers away from our capital, which is Canberra. So it's a country town. It's fairly small. There's no universities or a lot of science, which happens there. So it's not somewhere where I could go back to do what I'm doing now, but it's still home, which is nice. Such a small town. I think there were only 11 people in my primary school. 3 of the other people in the primary school were my brothers and sisters. So it gives you an idea of how small it was. I did my undergraduate degree in Sydney at UNSW, as was just mentioned, which was fantastic. UNSW is really powering ahead in terms of their chemistry development there. They're becoming one of the departments in Australia. I went on and did my PhD at ANU. Just a fun fact, I actually was doing my PhD as the same time as Prof. Masuri, who some of you might know. He's the head of the chemistry department at Diponegoro University in Malang. So that was a great place to do my PhD as well. And then I went on and did my postdocs in the UK, so Oxford University, some great chemistry coming out of there, and then Edinburgh with Polly Arnold. So that was great. And then finally I ended up in Singapore, as was mentioned, which is a great part of Southeast Asia. If you do want to find out more about my chemistry, as was mentioned, you can visit the chemistry website, rowdychemist.com, which is just an abbreviation of my name. And then there's more information on some of my research. Okay, so what am I talking about today? Okay, well, this is just a map of where I've been around the world. So, Griffith, Canberra, Sydney, all the way to the UK, and then coming back towards this part of the world in Singapore. Okay. So I guess the thing with Singapore is a lot of people know about it around the world, but they don't realize how small it is. So it's actually a bit of a hub in terms of Southeast Asia. So people from Australia or Europe know about it because often they might have their plane stopping in Singapore if they're traveling. A lot of the internet that we get in, say, Australia is routed through Singapore. So it's a bit of a trade hub as well. A lot of ships go through Singapore. So it's got a fairly large, I guess, footprint on a global scale, but it's actually amazingly small. So if you look at a map of Southeast Asia, you can see Indonesia, which is very large. But Singapore is really just a little red dot. And it actually took up the name Little Red Dot from a reference from Indonesia's president, who referred to Singapore as a red dot on Asia. So yeah, it's geographically very small, which makes it very conscious about some things. So for example, it's very conscious about I guess air quality. So I mean, you're probably familiar with air quality problems in Southeast Asia as well. Every few years we get the haze coming through, which is important. So this is more of an immediate concern with air pollution, but I guess longer term concerns with air pollution have got to do with global warming. And we have to take into account that Singapore is very low lying. So a lot of Singapore is actually reclaimed from the sea. All of these red areas used to be the ocean, used to be the sea, but Singapore imported soil a lot of the time from Indonesia to build up land around itself. So a lot of Singapore has been reclaimed from the sea, and most of Singapore is actually less than 15 meters above the sea. So I guess longer term air pollution effects, such as having global warming gases, are going to really affect Singapore because it's so low lying. Okay, so in terms of things we're concerned about here, global warming is one of them, which is going to become a theme for my talk, because I'll be talking about fluorocarbons today. What are fluorocarbons? How do they affect the environment? And how can my chemistry work into both of those problems? Okay, so first of all, fluorocarbons, we're probably using them every day, but maybe aren't familiar with it. Okay, so for example, some of the most common places we use fluorocarbons are in refrigerants. So the thing that makes your fridge cold, or the thing which makes your air conditioner cool, the gases in the air conditioner, the gases in the fridge are actually fluorocarbon gases. All right, so refrigerant gases make up the bulk of what we use fluorocarbons for, because refrigeration is everywhere, and refrigeration gases are needed everywhere as well. The next large sector is really polymers. Okay, so we're probably all familiar with Teflon. Okay, so maybe you've used a Teflon pan, a non-stick pan. So fluoropolymers are everywhere. Then we've got these smaller segments which are more specialized but very valuable. So for example, medicines, a lot of pharmaceuticals now have fluorine in them as well. It's becoming more recognized that fluorine plays an important biological role. The problem with fluorine, of course, especially in terms of the refrigerant gases, is that fluorinated chemicals, especially fluorinated gases, can be very environmentally harmful. They can either be toxic or they can be global warming gases. Okay, so the earlier fluorinated refrigerants, which are known as chlorofluorocarbons or CFCs, they were known for ozone depleting. So they were replaced with HCFCs, which are hydrochlorofluorocarbons, and hydrofluorocarbons, which are HFCs. Now, these things don't deplete the ozone, so we don't get a big hole in our ozone, but they are global warming. So they are contributing greatly to an increase in the temperature of the planet. As an example, most HFCs are at least 1,000 times more global warming than carbon dioxide. All right, so they're very potent. The current methods to destroy HFCs aren't very good. Okay, so one of the biggest uses of fluorocarbon gases is actually in fire extinguishers. Okay, because they don't burn, so they're very hard to destroy. When we do pyrolyze them, so under high temperatures, we generate a whole range of nasty byproducts. So there's actually a lot of research going into just how do we destroy these things without generating more problems. And of course, if we destroy them, there's no economic benefit in that. So we really want to get away from this situation where we've got this this increase in global warming gases, which is going to lead to an increase in the temperature of the planet. Okay, and we can see that even if we've replaced, say, CFCs with HFCs, the HFCs, the use is getting more and more and more. Okay, so we either have to stop using them, which isn't really an option at the moment because we rely upon air conditioning and refrigeration, or we have to reuse them. And that's basically what I want to do. Okay, so I want to take fluorocarbons, for example, global warming gases. I want to be able to collect them. So go to your house and take the gas from your air conditioner, replace it with new gas, take gases from old refrigerators, stuff like that. And I want to be able to use those gases as starting materials for fine chemicals. So I want to be able to functionalize them. So chemistry is functionalizing these gases to make valuable products. So for example, fine chemicals and polymer additives. And one of the biggest, I guess, benefits of doing this is that the chemicals that I make can have fluorine in them. A lot of the fluorocarbons that we use are actually polyfluorocarbons. They've got more than one fluorine. So we can see all of these commercial HFCs, so fluorinated gases, have got multiple fluorines in them. Okay, so if I can generate a product and I only have to say functionalize one fluorine, then I can retain all the other fluorine atoms in the product, which has a whole heap of benefits in terms of their biological activities or their waterproof activities or whatnot. Okay, now I just want to draw your attention to something here. So I've just put a sample of commercially available fluorocarbon gases. We can see some fluorocarbon gases, when we look at their carbon fluorine positions, the carbon fluorine positions are chemically equivalent. Okay, so for this example here, difluoromethane or R23, both of these CF bonds are the same. Oh, sorry, trifluoromethane. All of these CF bonds are the same. Okay, on the right-hand side, I've got a situation where the CF bonds are not the same. Okay, so for example, in this first molecule, R125, I've got a difluoromethyl group and a trifluoromethyl group. All right, so that's an important distinction, because when we go to do chemistry, if we've got equivalent CF sites, we only want to activate one, and that's very difficult. I'll show you in a second why. Okay, so the idea is to make these valuable products from fluorocarbon starting materials. Okay, and just as a quick example, this is the most common refrigerant gas used. Okay, so the chances are that your air conditioner is using this gas now, R134A. Now, if you want to buy this, because it's so widely used, it's very cheap. You pay less than $5 per kilogram to buy it. So when you pay for a top-up with your refrigerant gas, it doesn't cost you a whole heap of money. If you want to functionalize this, let's say if we wanted to functionalize this CF bond and retain this this trifluoromethyl group, and we wanted to stick it into, say, a polymer. So this is a polyacrylate type polymer with just this component, which is from here, or could be from here. We can see that this is actually quite expensive. If I go onto a chemical website and see what it's worth, this is just for 200 milligrams, 345 Singapore dollars. That works out at about $1.5 million per kilogram, right? So we can see just simply we can value add from a very cheap starting material to a specialized product. And even though most of the polymer fluoro market is actually Teflon, which we're all familiar with, this green one is Teflon, okay? There are a whole range of other fluorinated polymers out there which are gaining attraction, okay, for things like their lipophilic properties, all right? So they're very good at waterproofing things, all right? Then, of course, the other big area of value is pharmaceuticals, all right? So a lot of pharmaceuticals have got fluorine installed. The question is, can these fluorine atoms come from waste fluorocarbon starting materials, okay? Normally, when we stick fluorine into molecules like this, we have to use very toxic fluorinating reagents, things like hydrogen fluoride or fluorine gas, okay? So the question is, can we use very safe fluorocarbon starting materials to install these same fluorine molecules? Okay, so that's how it could be valued. Now, I'm just going to talk about one particular problem today and how we've solved that problem. We've done research on a whole different range of carbon fluorine functionalization and activation, but I just want to talk about one particular problem. And that problem is often called the overreaction problem. Now, when we've got a fluorocarbon, especially an aliphatic fluorocarbon, something like a trifluoromethyl group, or here we've got a tetrafluoromethyl group, where we've got equivalent CF bonds. All right, so in this example here, tetrafluoromethane, all of the carbon fluorine bonds are equivalent. The bonds are very strong, right? And some of that bond strength comes from the polarity of the carbon fluorine bond. Now, if we imagine this polarity as being fluorine being the most electronegative element, it would be delta negative. Carbon being a lot more electropositive would be delta positive. We can imagine that there's a lot of ionic character in this bond. Now, when we have other fluorine atoms on the carbon, because they're electron withdrawing, it makes the carbon more delta positive, which makes this bond even stronger. So what happens as we go from more fluorinated carbon positions to less fluorinated carbon positions, our bond strength goes down. Okay, so if we look at tetrafluoromethane, the bond dissociation energy, the bond strength, is 131 kcal per mole. When we replace one of the fluorines with hydrogen, the bond gets weaker. If we replace two of the fluorines with two hydrogens, the bond gets, each CF bond gets weaker. And then finally, if we just look at fluoromethane, this has got the weakest CF bond. So what happens is when we want to replace fluorine with any other group or any other atom, the remaining CF bonds become weaker, which means that the products become more reactive than the starting material. So for example, if I wanted to do a simple reaction, so if I wanted to take this molecule here, which is benzo trifluoride, and I wanted to replace one of my fluorines with bromine to generate this molecule here. So if I was trying to use, say, a common brominating reagent like boron bromide, if I took that, the first bromine would of course replace a fluorine, right? But then this would be my product, and this would be my starting material. The next equivalent of boron bromide, rather than reacting with starting material, it would react with the more reactive product, because this is a weaker CF bond to generate this product here. Now we've only got one fluorine, so this CF bond is weaker than both of these. So the next boron bromide would want to attack here. So I would get overreaction to the tri-brominated species because each of my products is more and more reactive. So when I go to do this reaction, if I say use 1/3 equivalent of boron bromide, right? So a stoichiometric reaction between these two, rather than getting 100% yield of this, which is what I want, I get a very low yield of my desired product, and most of my product is in fact the boron tribromide product, all right? Because the products are more reactive, right? So this was a long-standing problem, which no one had come up with a general solution. Now, I just want to take a look at how we do our chemistry just quickly before I go into how we're going to do it. There's really three ways of doing carbon fluorine activation or functionalization. You can use a metal, a transition metal, do oxidative addition chemistry. You can do radical chemistry with adding electrons or removing electrons, or you can do heterolytic cleavage using things like Lewis acids. And this is what we do. We use Lewis acids to do our chemistry. All right, so we focus on fluoride abstraction with the Lewis acid. So we're not taking F neutral, we're taking F minus. We're taking a fluoride, which is important for this type of solution. Okay, so what has been done in this area? Now, there have been a number of people who have tried to solve this problem of overreaction. So, for instance, this example here in Angevante in 2016, it's an example where they generate a silicium. So they remove the hydride from the silicon. They generate a reactive silicon, which reacts with the ortho trifluoromethyl group, which will then react with a nucleophile. All right. So this is a kinetic solution, in that rather than the active silicon, once they abstract the hydride, reacting with a product which is more reactive here, okay, it's got weaker CF bonds, it reacts with the closer CF bonds. So that's a kinetic solution. Now, it only works if you've got this ortho-silo group. So it's very restricted, and it only works for aryl CF3 groups. Some people have looked at using CF3 groups which are attached to carbonyl or olefin type positions. Now, with this reaction, you get a transfer of the double bond from this position to your CF position. So you generate a difluoroolefin. So you're generating this initially when you abstract a fluoride, but because the fluorine destabilizes this carbon position, the double bond migrates, and we get the double bond here, all right, which is why we get this product. Now, we're going from an sp3 CF bond to an sp2 CF bond. So in this situation, we know that sp2 CF bonds are stronger than sp3 CF bonds because sp2 bonds are stronger. All right, so this is a thermodynamic effect, but it only works when we've got this vicinal carbonyl or olefin group. There was a one-off example in ChemSci where they were able to do something called hydrodefluorination, turn one CF into a H selectively, using palladium and copper catalysis. They didn't understand why, and they've not really developed this. They can't put anything useful in there, only hydrogen. We really want to be able to stick a functional group in there. So that was a bit of a dead end. More recently, some people have looked at doing some radical chemistry. So CF3 groups are very electron withdrawing. So if our starting materials are electron poor, right? So they're actually better electron acceptors if we're going to do radical chemistry. So some people can do radical chemistry with these. This is quite restricted still in that we need to have an aryl CF3, and generally we need to have a very electron withdrawing group, right? And then lastly, there was this report by Stefan which used a selenium phosphenoadduct to try and trap the phosphonium salt of the difluoride. And because this was cationic, the next equivalent didn't want to attack there. It wanted to attack more benzoyl trifluoride. All right. So this was kind of the idea of what we were doing. This came out kind of similar time to when we started publishing this area. So our idea for how we could stop overreaction was basically we wanted to take a polyfluorocarbon, and we knew that there was nothing more electronegative than fluorine that we could put in, nothing more deactivating. So we said, okay, rather than sticking something that is an anion in, we'll put something which is neutral in. If we use a neutral base, our intermediate will be cationic. So if we have a cationic intermediate, then our Lewis acid will be repelled. It won't want to abstract any more fluorides because that would generate a dication, which would be a very high energy pathway. Once we convert all of our polyfluoride to this intermediate, then we can functionalize it. So that's the idea. Now, we knew that we had to use FLP chemistry, so frustrated Lewis pair chemistry, because we didn't want our Lewis acid to be locked up with our Lewis base. All right, so FLP chemistry is basically where I've got a Lewis acid and a Lewis base. Normally, they would form a Lewis adduct where they would stick together. We know from Lewis acid-base chemistry. But in cases where there's too much steric repulsion between the two, then they can't form an adduct and they remain unquenched. So the acid can go and do reactivity with something else, and the base with each other. All right, so that's what we needed here. We want the Lewis acid to react with our polyfluorocarbon, but not with our Lewis base. All right, so this was the general idea. How did it work? Well, we decided to do proof of concept with a very simple system. All right, so basically just a difluoromethyl group. So this is the difluoromethyl groups we started looking at, just using a simple FLP system. So using a triaryl phosphine and a triaryl borane system. So these two don't form an adduct, not a very strong adduct anyway. It's quite easy to break if they do form an adduct. The boron abstracts the fluorine from this, and the phosphine captures the intermediate. Right? So we get complete conversion, 100% conversion, very clean, to this phosphonium salt, where we've only activated one of the fluorines. All right, so we've activated it very clean. Our product is not more reactive than our starting material, which is fantastic. All right, so this is what it actually looks like. This is the crystal structure of the activated product. Keep in mind, this is a stoichiometric reaction. All right, so we could expand the scope of this. We can look at how far we can push this reaction for the difluoromethyl groups. So, for instance, difluoromethyl groups on aryl positions, we can generate our products very cleanly. Okay, so all these yields are quite high, really high conversions as well. We can extend this to heteroaromatic systems, like a furan system. Pyridine didn't work, but it was for a different reason. So basically, this gets deprotonated rather than having CF bond activation. It works a little bit with aliphatic systems as well. Okay, we've improved this since. All right, so it kind of works as a general route to selective CF activation, difluoromethyl groups, which was great. So this was from a few years ago. We can take these types of products, and because we've got this alpha CH position in a phosphonium salt, the obvious thing to do when we wanted to functionalize was to do a avidic olefination. All right, so taking these, reacting with base, then reacting with an aldehyde to generate fluoroolefin products. And we could do that with a whole different range of phosphonium salts and a whole different range of aldehydes to generate these types of products. Okay, I'm just going to ask the moderator who drew on the screen, would you be able to delete that? Hello?
Wait a minute.
Yeah.
How to delete?
But sometimes it happens.
Okay. I guess we can keep going. It's only small, but I thought you might. Yeah, I think it came from Addy's screen, the host. Yeah.
Really?
Anyway, we'll keep going.
Okay.
All right. So these are the people who were doing the chemistry on this. So we showed that this worked quite well for difluoromethyl groups. The real question is, can we make it work for trifluoromethyl groups? Because trifluoromethyl groups are utilized a lot in organic chemistry. All right, they're more difficult to activate. Remember, the more fluorines that we have on a carbon position, the stronger the CF bonds. All right, so we showed proof of concept for difluoromethyl groups, but trifluoromethyl groups, the CF bonds are quite strong. All right, but that's the one that we really want to be able to functionalize selectively. All right, now when we apply the same protocol where we take our Lewis acid, so this is just abbreviated BCF for our Lewis acid, and our Lewis base, and we try doing the exact same reaction that I showed you just previously, nothing happens. All right, in the last reaction, all these reactions were carried out at room temperature. Okay, in this situation, room temperature, no reaction will occur. If we heat it up, okay, maybe after 2 days, we get a little bit of yield, 20% of our product. Not fantastic, definitely not good enough to be useful. All right, 20% under these conditions after 2 days is not very attractive. So it's not very selective. But we thought maybe if we can regenerate our Lewis acid, we can make this more active. Right? So our Lewis acid is getting tied up because it abstracts the fluoride and generates the anion. So we thought if we can make this catalytic, maybe we can make it more reactive. So the idea was we have our Lewis acid, it abstracts the fluoride, and our Lewis base picks that up. So we generate a phosphonium intermediate, and then we want to regenerate our Lewis acid, which is locked up with this fluoride. So we wanted to add some additive that would lose fluorine from our Lewis acid, generate this product, and regenerate our Lewis acid. So our Lewis acid could be catalytic. Right, so we tried doing proof of concept of this. So we could actually make our Lewis acid with fluorine in there by reacting with cesium fluoride. And then we were able to react that with a range of additives, right? So the obvious ones to try were TMS additives, because silicon and fluorine form a very strong bond, and TMS fluoride is actually a gas, all right? So these two react together when we have triflate or triflamide as our TMSX reagent. They regenerate our Lewis acid, and we get TMS fluoride gas, which is fantastic. So we tried all of these additives. We tried things which we thought would drop the fluorine out of solution. So lithium fluoride is quite insoluble. So we tried lithium type reagents. Some lithium salts gave a little bit of product. The triflate reaction didn't really work, even though it did work up here. But the TMS triflamide worked really well. All right, so we got basically at room temperature after a day, we got 86% yield of our desired phosphonium salt. All right, so at room temperature, nothing works here. Doesn't matter how long you leave it. Here, with only 21% of BCF, so catalytic amount, after a day, we get 86% using our triflamide. All right, so that was a good hit. We could develop that. Okay, so we could improve upon that. If we heated it a little in a much shorter time with very low loading, so only 5 mol% loading, we could get pretty much quantitative yield. All right, so this becomes quite useful in terms of doing chemistry. If you can get quantitative selective CF bond activation after 12 hours with a small catalyst loading, that's quite good. This is with heating. If we increase the loading to say 20 mol%, we can do this reaction in just a few hours. Okay, so this becomes very useful. It means that you can do selective activations just in a morning or afternoon rather than have to leave the reaction overnight. Okay, so our TMS triflamide, basically its role is to regenerate the Lewis acid. It reacts with the BCF fluoride, generates TMS fluoride as a gas. The triflamide becomes a counteranion, and we regenerate our Lewis acid. All right, so this is the model product that we're looking at here. All right, so that's fantastic. We can apply that to a whole different range of phosphonium salts again. So we can do selective CF activation in trifluoromethyl groups. So this is a range of different trifluoromethyl groups that we can show we can do this for. It works for hetero aromatics, so in the presence of furans or pyridines. It works for di or bis trifluoromethyl type substrates, which are very difficult to activate. So it's very electron withdrawing groups make these CF bonds very strong. But it also works for non-aromatic groups. So we can put this onto, say, a methoxy or a thiamethoxy trifluoromethyl position, and it still works quite well, right? So it's actually applicable to a lot of different CF3 groups. All right, so that's fantastic. Now the problem is, in the last paper, we saw that when one of these atoms was a hydrogen, we could do a avidic olefination and make a double bond, a fluoroolefin. But when we have phosphorus, there's less opportunities. Okay, so with phosphorus chemistry, if I install phosphorus as my base here for my selective activation, you can do avidic chemistry, avidic olefination if that's hydrogen. But if we've got two fluorines, we can't do as much. You can do some radical chemistry, which I'll show you later, and some other types of functionalizations, but you can't do palladium coupling chemistry, which is very useful in organic chemistry. You can't even do simple nucleophilic substitutions, right? If we look at sulfide or nitrogen type bases, so if we look at simple sulfides or pyridines or amines as bases, there are reports of these being able to do all of these things, not for the difluoro salts, of course, but for other ammonium salts or pyridinium salts. These have been reported. Right, so we thought maybe we should change our base from phosphine to something else, which allows more functionalization chemistry. All right, so just as an example, as I was saying, phosphonium salts, you can't do, say, a Suzuki coupling, but for sulfonium salts, ammonium salts, and pyridinium salts, there's reports of Suzuki couplings for all of these. All right, so we thought this might be a better thing to aim for. All right, so how do we go? Well, if we try replacing a base, instead of using phosphine, we tried a whole different range of bases. The sulfides didn't work, the amines didn't work, pyridine didn't work. When we used lutein, we got a little bit of yield, maybe 10% of our product. But when we put in much larger protecting groups, so this triphenol pyridinium salt, we actually got a fairly decent yield, 67%, room temperature 24 hours. Now, if we leave that for longer, it's actually a very clean reaction. So if we leave it for longer, we get pretty much quantitative yield at room temperature using this triphenyl pyridinium salt. All right. If we want the reaction to go faster, of course, we can heat it. In 4 hours, we get a decent yield. But these salts aren't as stable as the phosphonium salts, so it does decompose just a little bit. All right. So generally, we do these reactions at room temperature, so we get quantitative yield. We want the highest yield. Now, the useful thing is that this base, we didn't choose it by accident. There was actually a lot of literature out there surrounding this triphenyl pyridinium group, or this triphenyl pyridine base as a leaving group. All right, so it's known to be able to do simple nucleophilic substitutions. People have shown you can do alkylation chemistry. You can do Suzuki couplings, reductive couplings, so that's similar to palladium chemistry. You can do borylation, so you can stick anything in here. So you can stick in heteroatoms, carbon-carbon bonds, boron, whatever you want. All right. The question is, can you do it when there's fluorine there as well? All right. So this is a useful group to have in there. We showed just simply that we can take a trifluoromethyl group, that we can do our activation chemistry, and then we can just do a simple nucleophilic substitution. And this, even though it's a very simple reaction, is something which could not be done at all before. There was no way of doing a selective nucleophilic substitution of a trifluoromethyl group. But here we can see we can get very good yields. For simple halide substitution, we can get, these are conservative. There was actually above 80% for all of these types of products. We can stick in a whole different range of heteroatoms. Any type of base you can think you can stick in, because this pyridinium group, this pyridine group, is actually a very good leaving group. All right, it falls off very easily. All right, so we can stick in a whole different range of heteroatoms just using SN2 nucleophilic substitution. Okay, we can do carbon-carbon bond formation reactions. So, for example, we saw that there was this phosphonium coupling type reaction out there. It was called a nucleophilic transfer reaction, published a few years ago in Nature Communications. So we tried to see if we could apply that to our systems, and we could. So when we got phosphine in there, we can form a carbon-carbon bond, generating an alpha alcohol. This works fairly well. If we've got either our phosphine or our pyridine base in here, we can do alkylation chemistry, right? So with an alkene, we can do photoredox chemistry, where we can react that alkene across here, so we can do CC bond formation reactions like that. We can do Suzuki couplings. As I was saying, the pyridinium groups are known to do Suzuki couplings, right? So if I've got the pyridinium group there, I can use a boronic acid to install different aromatic groups. So these are CC couplings. Works for if I've got an activated difluoromethyl group or an activated trifluoromethyl group. And of course, we can do something as simple as doing a hydrodefluorination. It's where we've just replaced our fluorine with a hydrogen, okay? Which seems like a very simple reaction, but is hard to do selectively. Whereas when we do it, we basically get quantitative hydrodefluorination using our approach, right? So by selectively capturing our activated difluoro and trifluoromethyl fragments, we can do a whole different range of functionalization chemistry after. All right. How does the reaction work? Why is it so facile? Why does it work when it's catalytic? Okay. We didn't know the answers to this, to tell you the truth. But there was someone else in Spain, a guy called Israel Fernandez, who was interested in our chemistry and wanted to work out why it worked. Remember, the CF3 bonds are much stronger. We weren't expecting a Lewis acid like this borane Lewis acid to be able to abstract the fluoride from a CF3 group, because the fluorine bonds there are very strong. And of course, if we didn't do this catalytically, it didn't work at all. Now, what we didn't realize is that the reaction has actually got a fairly low barrier. And it's got a low barrier because our base, our triphenyl pyridine base, actually assists the fluoride abstraction. So this guy, Israel Fernandez, had a paper come out just a few weeks ago, and he showed that the activation barrier, if the base is assisting to remove that fluoride, is much lowered in this situation. Okay, and you have got to have to look at these numbers in the brackets as well. Okay, because these numbers don't account for entropy; they're just enthalpy numbers. But when he looks at free energy, he has to include entropy. You get the numbers in brackets, and we see the numbers in brackets. So our product, negative 0.06 kcal per mole, and our starting material, which is 0, they're very similar. What that means is actually we get an equilibrium. Okay, so the reason why this needs to be catalytic is because when we get this equilibrium, we don't get all of our starting material becoming product. It just goes back and forth. So when we react our TMS trifluoride with this this product here, it basically takes the fluorine out of the reaction and allows the reaction to turn over. So what we get is this equilibrium forming, which was calculated here by Fernandez, because the BCF fluoride can act as a nucleophile as well to reform our starting material, and the TMS trifluoride is needed to remove this fluorine and kick the reaction over. All right, so that we can go all the way to our desired product. Right, so the important points that he discovered were the bases needed to lower the activation energy of removing the fluorine, and that to overcome this equilibrium, we need the TMS trifluoride to drive the reaction forward. Right, so we can see that this reaction, which we wouldn't expect to work at all with these strong CF bonds, actually works because of the FLP cooperativity in this this reaction. All right, so just a quick summary of what I've talked about today. So we've looked at the difluoromethyl groups and trifluoromethyl groups where we've got equivalent carbon fluorine positions. Normally, if we tried to functionalize those, we would get overreaction. But using FLP CF bond activation, we can isolate the intermediates in pretty much quantitative yield. Okay, so we get selective CF bond activation. So only one CF bond gets activated to generate this fluoroalkyl product here and these difluoroalkyl products here. And then we can do functionalization of these to generate a whole different range of products. All right, so this is a very general way of doing CF bond activation. It works on almost any difluoromethyl or trifluoromethyl group. We wrote a short review or a short summary of this chemistry earlier this year in SYNLET. So if you're interested, have a read of that. And it's got a nice overview of the chemistry. I guess lastly, I just want to thank the people who've done this. Okay, so this is the group. Dipendu, Richa and Amit have done most of this work. Okay, just a few people I'm going to thank for the funding as well. And if you're interested, like I said, check out the internet site, 𝐷𝐻𝑒.com. Of course, 𝐷𝐻𝑒 comes from just an abbreviation of my name. Okay, fantastic. So that's the end of the presentation. Hopefully, we've still got some time for questions. So I'll just stop sharing my screen there, and I'll give the mic back to the moderator.
Okay. Okay, thank you very much, Dr. Pawan. This is quite interesting, and it's actually a very organic chemistry, yeah, because it's all about say a synthesis of CF, including CF bonds. So there are so many questions here. Okay, maybe the first one. Can you describe in detail how synthesized alkyl fluoride, a very important precursor molecule for your valuable fluoride-based molecule production? As you know, that fluorine gas is a very corrosive.
Yep, that's a great question. Okay, so when we install fluorine into organic molecules, there is really no way of escaping doing some nasty chemistry. Okay, so if you are making a refrigerant to put in your air conditioner, or if you're making a pharmaceutical drug, okay, you can do that with toxic fluorine. Okay, so for example, if you're making a refrigerant, it's a very simple molecule, something like tetrafluoromethane. So in that situation, people would just use fluorine gas with, say, methane, and they would just do that under extremely harsh conditions. The byproducts are toxic, of course, and the chemistry is not very friendly, but it's done on a very large industrial scale. So these things, they can't be avoided. So what we're saying is we can't avoid installing fluorine through some nasty process. But what we want to do is we want to avoid doing it as much as we can, right? So if I've installed fluorine into an organic molecule using some nasty process, okay, I can either take that molecule, which already has fluorine in it, and recycle it, okay, and then use that recycled fluorine, which is what we're trying to do, okay? So when we put fluorine into a molecule, it's from a recycled fluorine, or I can take another fluorinating reagent, which is a toxic reagent, and install fluorine from scratch. The problems with doing that, so if I'm making, say, a pharmaceutical drug and I want to use a fluorinating reagent, one, it's toxic, okay, and dangerous to use. Two, it's got very poor functional group tolerance, okay? It wants to react with lots of different things, okay? It's very hard to selectively put it in. That's why fluorinating something simple like methane is not a problem. You can use harsh conditions. If you want to fluorinate your expensive pharmaceutical compound, it might not tolerate these same conditions, okay? So yes, you've got to use toxic fluorine or toxic hydrogen fluoride to get the fluorine in at the start. But what we're doing is we're trying to take fluorinated compounds which have already been created for other purposes. They've been created to be used as refrigerants and reuse those so that we don't have to go through that fluorination step again. Okay, somewhere along the line it has to happen, but what we were trying to do is say it doesn't have to happen twice, and when it does happen, it can happen with very simple molecules which can undergo these harsh conditions. We don't have to use more expensive and elaborate fluorinating reagents which can tolerate pharmaceutical drugs, for example. Hopefully that answers the question a bit. Do you want to feed the questions to me one at a time, or do you want me to just go through the chat and answer them as we go?
Okay, maybe the next question. Mr. Adi, could you please tell? Okay.
Do we need specific catalysts to generate specific product in certain reactions? The catalyst that we've been using is quite generic. So one of the things that we've concentrated on, and one of the good things that we've done, is that we've used components which are all commercially available. So the boron Lewis acid, which is our catalyst, is actually commercially available. It's very easy to buy. You can go to many different chemical companies. I mean, 𝐷𝐸 in Singapore keeps it in stock all the time. Lots of groups around the world use it because it's commercially available. Our bases, so our pyridine base and our phosphine bases, are all commercially available. Every one of our components you can buy. You don't have to make anything. So any organic chemist can buy all of our components to do our reaction and just stick them into their reaction vessel, do the reaction to effectively make what they want. What I would say is that for some of our very, very difficult substrates, so for example, if I have alkylated substrates without an A-ring group there, the CF bonds become very strong. And for those examples, we actually do have another catalyst, which is even better at pulling fluorine off, that we sometimes use, but that one we do actually have to make. It's the same as the boron catalyst, but we've just replaced boron with aluminium. We have to make that one, so it's a bit harder, but it's, yeah, the catalysts are very available. Do you want to go to the next question, Adi? How do you use electrochemical methods in the synthesis? Okay, so basically the redox chemistry was something which was done a long time ago, back in the 80s. A guy discovered that you could do electrochemical reactions with these trifluoroaryl type substrates. And what he discovered was the trifluoromethyl group is very electron withdrawing. So it makes the arene more electron deficient, which means it's a better electron acceptor. So if you're trying to run a current across a solution, the electrons will jump into, say, an electron deficient arene, and you generate a radical. The product, which is the difluoromethyl arenes, are less electron deficient and are less likely to accept an electron. So originally this stuff was done in the 80s with electrochemical methods. So that's where you just stick in two anodes, or an anode and a cathode, so two electrodes, and you run a current through to generate your intermediates to do your chemistry. People have taken that and then they've used photoredox catalysis, which basically means that they use a small catalyst which gets excited by light, and the light makes it lose an electron. Okay, the electron, when it leaves the photoredox catalyst, it jumps onto the most electron deficient thing, which happens to be the trifluoroaryl type molecules. When they become radicals, they can then be functionalized through radical chemistry, normally through reactions, or actually every time through reactions with alkenes. So radicals can add across alkenes. So in that way, they've been able to selectively activate trifluoromethyl aryl type substrates, but only very electron poor ones. If you put an electron donating group onto the arene, it just kills the chemistry because electrons don't want to jump onto that anymore. Hopefully that answers it. the position of group in phenyl, like ortho or para, is it affected as well? Well, in our chemistry, if we have substituents in these positions, they will affect the chemistry, of course, okay? Because if we have it in the, say, para position, we get an electronic effect, okay? So because we're removing a CF bond, I'll just share my screen to emphasize this, I think. Let's look at some simple stuff. Here we go. So here we can see that when we've got electron donating groups like a methyl or an ethoxy or just a hydrogen, the reaction works quite well. If we put in something electron withdrawing, like a CF3 group, we get much lower yields. Okay, and that's basically because the CF bonds are harder to break. Okay, when we've got an electron withdrawing group here, it makes the CF bond stronger, and it's harder for it to break. So you can see that in this here as well, when we've got, say, electron withdrawing groups like chloride or bromide, we get lower yields as well. Donating groups like a methyl group, we get fairly good yields. All right. In the ortho group, we also have to be aware of steric effects. Okay, so if we've got a large group in that ortho position, then we're going to have a steric effect as well, and it affects the ability of the base to come in to trap our intermediate. So then we typically get lower yields as well. Okay, so yes, to a degree, what we have in the ortho and para position, it won't stop the chemistry, but it will affect our yields. So I can predict if the yield is going to be better or worse based on what's in those positions. But we can change our reaction conditions to get around that. So for example, a lot of these reactions, if they were poor yields like this, if we repeated them at slightly elevated temperatures, maybe 60 degrees rather than room temperature, we could get good yields for that as well. So I'll just stop sharing. Adi, do you want to share your screen again? Is there another question? Why is it called a frustrated Lewis pair? Well, this is a term which was coined by a guy called Douglas Stephan, who developed the field about 15 years ago. And it's called frustrated Lewis pair because normally a Lewis pair would combine to form an adduct. Now, you get frustrated when you can't do what you want to do. If a Lewis acid and a Lewis base, they want to form an adduct, but they can't, then we would say that they would be frustrated, because frustrated just comes about from not being able to do what you want to do. So how do we isolate the products? Well, one of the great things about this reaction is that all of our components at the start are neutral. All right, so when we look at our bases, our Lewis acids, our additive, which is TMS trifluoride, our starting material, they're all neutral, which means they're all soluble in organic solvents. Our products are all salts. When we displace that fluoride, we generate phosphonium salts or pyridinium salts. So our products have got much less solubility than our starting materials. So in many instances, we can just crystallize our products out, okay? Or sometimes we just do the functionalization reaction in the same reaction vessel. We don't need to isolate our intermediates. And if we do that, then we can just use column chromatography to get to our final functionalized products. But yeah, because they're salts, it's very easy to isolate them. So how do we know that the product yields? All right, so what we do is we normally use fluorine NMR. So fluorine is 100% NMR active. And we'll inject a fluorine standard, something which has got fluorine in it, but we know won't react, okay? So for example, fluorobenzene, an sp2 fluorine, doesn't work in our reaction, but because it's got a fluorine, we can see it in the NMR spectrum. So if we put in exactly one equivalent of our standard, then we can see when we integrate our NMR spectrum, how much of our product is left or is there, how much of our starting material is left when we compare it to our internal standard. So we use fluorine NMR to measure how much of our product is generated. Yeah. Yep, so this is a good point. So Hammett equation can be used to study the effect of, it actually can't be used for the ortho, but it can be used for the para. So Hammett equation is useful for para and meta substituents. Do we have research? We've actually already done that. There's a paper. So at the end, I was talking about some mechanistic stuff there, which is being done by a guy in Spain called Israel Fernandez. He did that mechanistic study by himself, just based on computational chemistry using DFT. What we've done is we've actually done the Hammett plots, okay, and we've done a lot of kinetic reactions, and we're going to publish that soon. It kind of backs up what his results are as well. Okay, so it backs up the fact that the CF bond activation step is the rate limiting step in this reaction. Okay, so the Hammett plot can tell you if it's going to be SN1 or SN2, and we've got those results, and we will publish them soon. Okay, but that's a very good suggestion, and that's what we wanted to do, and we've done that already. So thank you for the suggestion. Hopefully, I'll have that research out early next year. So how many instruments do we need to judge the results? Well, ideally, only one. We could judge results simply by NMR spectroscopy. That gives us a good idea about the identification of our product, its purity, okay, and then its conformation. We do a lot of other methods as well. So we do look at obtaining crystal structures, so we can look at the connectivity of the atoms. We look at doing elemental analysis as another measure of purity. So yeah, there's a lot of instruments that we do use, but you could, if you just wanted to generate these types of products, and you wanted to have a good idea if they were new products, then you could just do use NMR spectroscopy. If you had a very basic lab and you just wanted to use our method to make a certain chemical, if that chemical was already known, then you wouldn't need any instruments at all. You could just use chromatography, so thin layer TLC chromatography, to determine if what you had made using our method was the same as your desired product if you had a sample of that product. Okay, so that could be done by chromatography. But yeah, if you're making something new which you don't have an authentic sample of, then NMR spectroscopy is the best way. Okay.
I think it's enough, and the time is already 10 o'clock, 10 a.m. Okay, so thank you very much, Dr. Rowan. I hope to see you again, maybe next year, or maybe after COVID-19 goes away, we can meet offline. Maybe you can come to here in Diponegoro University, probably. So if anyone who is interested in Dr. Rowan research, maybe you can just send email. Is it okay, Dr. Rowan?
Yeah, of course.
Yeah. Or maybe you have any more question relating to his research interest. So you can just send his email. And then thank you for all participants here. Maybe we can see you later in next year. So we will have another webinar series also in next year. So thank you very much for your attention and also for coming here. Thank you and see you later.
Okay, thank you. I look forward to your invite, and yeah, thank you for the invitation, and feel free to email me any questions you might have. Okay.
Okay, thank you, Dr. Rowan. Bye.
Bye. Terima kasih Bapak Ibu atas kehadirannya. Insya Allah kita akan mengadakan lagi webinar ini tanggal 13 Januari 2021. Jadi tolong diagendakan setiap hari Rabu. Berarti hari Rabu pekan kedua ya. Jadi hari Rabu pekan kedua kita akan mengadakan setiap hari Rabu pekan kedua gitu ya. Pelaksanaan webinar series ini yang hari ini yang sudah yang kelima, insya Allah bulan Januari nanti yang keenam. Mohon diagendakan saja sebagai agenda rutin setiap hari Rabu antara jam 9 jam 10. Insya Allah pembicara berikutnya akan kami hubungi dari Amerika, dari University of Washington. Rencana kami akan menghubungi Dr. 𝐬𝐿𝐿𝐴. Topiknya masih agak-agak anorganik begitu. Tapi kami berusaha dari informasi dari perkembangan yang sudah ada selama 5 kali webinar ini. Yang pertama dari Australia, pembicara yang kedua itu dari Korea, pembicara yang ketiga dari UK, pembicaraan yang keempat bulan lalu dari Jepang, yang tahun ini yang hari ini dari Singapura walaupun beliau adalah orang Australia. Kemudian insya Allah bulan depan dari Amerika. Ya, insya Allah. Kita berusaha untuk kemudian mencari dari berbagai universitas, dari berbagai negara, dari berbagai macam topik ya. Topiknya ada yang biokimia, ada yang hari ini sangat organik, sebelumnya ada yang sangat anorganik gitu ya. Jadi diusahakan segala topik. Jadi Bapak Ibu selalu stay tune dengan agenda webinar JKSA dan yang lain, mungkin sedikit sponsor. Kami mengundang Bapak Ibu untuk kemudian submit paper Bapak Ibu ke Jurnal Kimia Sains dan Aplikasi. Ini jurnal yang terbit sebulan sekali di Sinta, berada dalam akreditasi Sinta 2, dan kami sedang berusaha untuk kemudian menuju ke Scopus dan juga terindeks di SC. Mungkin begitu, terima kasih Bapak Ibu atas kehadirannya. Bagi yang membutuhkan sertifikat bisa mengisi link di di kolom chat, sudah saya posting, tinggal di link, dan kami hanya bisa sending 100 sertifikat untuk hari ini. Kalau misalnya lebih dari 100 sertifikat berarti kami akan kirim sisanya besok. Mungkin begitu, saya akhiri. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih Pak Adi dan teman-teman.